All right, so general syllabus stuff. You guys are all literate, so whatever. I'm still me. I'm still an asshole. Nefkin 211 is my office. Tuesday through Friday office hours 2 to 4:30 p.m. From 3:30 to 4:30 on Tuesdays and Thursdays, I'll actually be downstairs in Nefkin room 120 doing the general tutoring help sessions and all of that kind of stuff. So I just wanted to make you aware of it. I will be in the building, just not in my office. My email address is still just my last name at latech.edu. And there's my phone number. It's completely worthless because I teach so many damn classes. I'm never there unless it's during office hours. General boilerplate class disruption emergency thing. If, I don't know, we get COVID 2025, we'll continue the class over Canvas and Zoom. Usually for weather events, they just cancel classes. So anyway, if they tell me to, I'm ready to switch to online, whatever. Course objectives, we are going to learn a whole heck of a lot about how magnetic fields behave as a medium for electromechanical energy conversion. And then we're going to talk specifically about some devices that rely on that, like relays and motors and all that kind of good thing. The textbook for this class, I don't even know what the hell it says online anymore. I think I changed it to this PC Send textbook. I hope I did because it's actually pretty reasonable. You don't need to buy it or actually have it, but a little birdie told me that you can definitely download it online. Don't know how I figured that out. If for whatever reason the official textbook of this course on, I don't know, the bookstore or whatever is the Gonin book, that thing is just hot garbage. So definitely, if you're going to illegally download anything, download Principles of Electric Machines and Power Electronics by PC Set. Let's see, disability disclosure. If you have a learning disability, sign up through the Office of Disability Services and make sure that you get your extra time and all that kind of good stuff. Class attendance is the same as it's been before. Obviously, I've got things on Zoom. I'm recording it. So if you don't want to be here, don't. That's your prerogative. The only thing I'll use attendance for is at the end of the quarter. If you're, borderline between two different letter grades, I'll look at your attendance and stuff like that and be like, hey, they showed up. They were trying. Maybe I'll be nice and give them a bump. Whereas if you never show up, I don't know who the hell you are, then your grade's your grade. Honor code stuff, boilerplate, behavior, be less of a jerk than I am, don't cheat. Homeworks, feel like this is pretty much the same homework policy that I had in the 280 course. Brief-ish homework set, 3 to 5 problems will be assigned to Canvas at the end of most lectures. I'm expecting if I assign it on a Thursday, it'll be due the following Thursday kind of thing. At midnight, anything that's late incurs a 20% penalty for each day that it's late. Make sure that me, more realistically, my grader can actually read it. Let's see, exams. There are going to be 3 tests. I'm actually thinking about something on this, and so I'll talk with you guys about it and see how you feel. So in most of my electrical engineering courses, particularly my sophomore and excuse me, not my sophomore, my junior and senior level classes, I usually do an in-class portion of a test that's worth anywhere from 50 to 75% of the test grade, and then a take-home portion of the test that's worth whatever's left out of 100%. So the in-class portion is meant to be able to be done in class, quite obviously. It's a couple of problems of what I would consider easy to medium difficulty, but there is a time constraint, so you have to manage your time and be able to do everything. And then I usually assign 1 to 2 hard problems as a take-home portion, where the expectation there is that you might have to use like computer algebra tools and things like that to be able to figure stuff out. I haven't done that for any of my ICT classes yet, but I'm considering that, so I just want to know what you guys' thoughts are.
I'm down for it. I like one challenge.
Okay.
Just take what I'm given.
Okay.
Here for you to grade, so they're grade back, or the grade is to grade, so we get our stuff back.
So only having one thing to grade would be the fastest thing for my grader to grade. So, okay, I'll stick with just the regular normal test for now then. All right. Don't use your phone during an exam unless you want to fail. Weighting of grades, homeworks are 30%. So you really need to do your homeworks in this class to pass. The in-class assignments are worth 10%, and then exams 1, 2, and 3 are each worth 25%. The exam that you score the lowest on, its weight will be reduced down to 15%, so that all of that adds together to make, I don't remember if it's 100 or 105, but it's not well over 100, so a normal thing. Traditional 10-point grading scale, officially no curving or rounding of grades, but we already talked about your not your appendix, your attendance will be used to scale things if you're on the borderline. Yeah, whether or not you've had appendicitis will in some way, in shape or form, influence your grade in this course, apparently. Excuse me. All right, syllabus changes. I don't expect the syllabus to need to change, but I reserve the right to do so. More information about the emergency notification system, COVID-19 policy. Generally think of this as just an illness policy. If you're sick, don't come get me sick or I will be pissed off. Everything will be available on Zoom and my shitty YouTube channel. Stay away from me if you're ill. I will be so mad. Okay. If you need counseling services, they are available to you at no cost. There's not really any particular opportunity for you to have to use AI or anything in this particular class, but I do have a policy for it, just to cover my ass. And then our tentative course schedule today, we're going to talk about syllabus, which we've already done. Review some magnetic field stuff, probably going to be significantly different than how you guys covered E&M related things in your prior physics classes, because you guys take like a trig-based physics, right?
Yeah, we take the norm.
Let's say you take 209, 210, which.
Yeah, that's physics for poet. That shit's garbage.
Yeah.
Yeah. So, that's very much not true. That being said, calculus makes it wildly easier. So I'm going to be, when I have to use any electromagnetic field theory, I'm going to use the calculus-based version of it, but I will talk you through what it means in the context of what we're doing. So it's not going to be just, oh God, I don't know what any of this shit means. I will explain it to you in a way that you should be able to catch what I'm throwing relatively easily. But that trig-based physics is hot garbage. In my opinion, trig-based physics is much more difficult than calculus-based physics. So anyway, that's enough of a rant about that. All right, so any questions, comments, concerns about the syllabus before we get into things?
I'd like to revisit the testing,
Okay.
because like, I feel like we could do a trial run of it for the first half and see how people like it.
Okay.
Because I think the take-home portion of the harder problem would be beneficial for everybody.
Okay.
I feel like it'd be a good.
I'm willing to do it for exam 1, and if you guys just absolutely hate it, we go back to normal for the subsequent exams. I got no beef with that. I have to remember to, make out a quote unquote hard problem and all that kind of stuff, but I've got a month to do it. I'll probably get it done. We'll see. Yeah. Worst case scenario, I say I forgot we're doing what it says on the syllabus. Anyway. All right. Any other things? Okay. So, let's get to it then. All right. So let's call this review of magnetic fields and magnetism. All right. So before we get into just a bunch of gross math, I want to talk to you guys about why we are discussing magnetic fields in particular today. Right? And the short answer is the overwhelming majority of electromechanical energy conversion devices, so things like relays, induction and synchronous motors, even DC motors, DC brushless motors, all of that kind of good stuff, rely on effectively a magnetic field to do one of two things. It's either going to store energy that's used to convert into mechanical energy or electrical energy, vice versa, because we have electromechanical transduction. So that means effectively the transfer of energy can go in both directions. We can convert from mechanical energy, turning something, et cetera, store energy in a field, and then use that to create an electrical signal. Or we can go the other way around and we can apply electricity, store that, and then convert that stored energy into mechanical energy. And so since we have to focus so much on a magnetic field's ability to either store energy or be able to induce torques and things like that in physical systems, we need to have a pretty damn good understanding of how magnetic fields behave. And so we're going to take today to revisit all of the stuff that you learned in your physics class, and hopefully you'll come out with a better understanding of what's going on. So we'll start by saying that are generated by electrical currents. So effectively, anytime we have an electrical current flowing through any medium, we are going to create a magnetic field, okay? And the equations that relate these two quantities, so magnetic fields and current, are, and so here's our first gross math equation. So I have a line integral or a contour integral, H dotted into DL is equal to J, excuse me, a surface integral of J dotted into dA. And this is what's called Ampere's circuital law. And then my second relationship, and actually I'm going to give myself some space where I'll talk about what those things are here in a moment. And so my second relationship is I have a closed surface integral of B dotted into dA is equal to 0. And this guy is known as Gauss's law for magnetism. Zero. B dot dA, or the integral of B dot dA is equal to 0. Okay. So I don't know for sure, but I'm 99% positive that you guys probably have very limited exposure, if any, to line integrals or contour integrals and surface integrals. Am I right in that assumption?
I've never seen it before.
Okay, so got some people saying they've never seen it before in their life. Okay, so before we get into what this math means, let's talk about what the different parts of things are, okay? So for this guy right here, and I probably actually, sorry, I'm going to move this. Oh, you're writing in a notebook. I feel like a dick. I won't move it. So H is the magnetic field strength vector, okay? So this is effectively the amount of magnetic field that we as engineers have some control over, and it effectively depends on how much current we apply in a system, okay? Then we have L, actually, and this is measured in amps per meter. And then J is a current density vector. And it's measured in amps per meter squared. Okay. And then for our second equation, this vector B is the magnetic flux density vector. And it's measured in Tesla. So I'm going to go ahead and write this out. Tesla T, where 1 Tesla is equal to 1 Weber per meter squared. And I understand that you guys probably don't know what a Weber is. We'll talk about that in a minute. It can also be written as 1 volt second per meter squared, because a volt second is simply a Weber, or it could be written as 1 joule per ampere meter squared. So we got lots of different conversions to go between Tesla and things that we are familiar with. Okay. So let's talk about these equations, okay? So Ampere's circuital law states that the line integral, so that's what, whenever I have an integral with a subscript C, all that means is that I'm integrating along some path or some contour, and that's what the C stands for. This circle thing right here means that I have a closed line integral, meaning that I'm integrating along some closed path. So if I have a contour that starts and ends at the same point, like a circle or a rectangular path or something like that, that's a closed line integral, okay? So that DL thing is just a differential line element or a small part of that path or contour that I'm integrating along, okay? So I'm integrating the magnetic field vector along some closed path, and it is equal to a surface integral of J dot dA. So let's talk about that bit right there, okay? So a surface integral is effectively me integrating over the surface of something. In this case, I'm going to be integrating over the surface that is defined by my closed contour, okay? So if I draw a circle around something, I should be able to integrate over the surface that is defined by that circle. That's all this means, okay? And I'm integrating my current density vector with respect to some differential area. So some small part of that surface that is bounded by the contour. So all of this hippie crazy math jargon effectively says is that the integral of my magnetic field around some closed path is equal to the total amount of current that flows through that closed path. That's what that big ugly integral thing says. Okay. Equation 2, I have my magnetic flux density vector integrated with respect to some other differential area element, right? So I've got a surface integral, but now I'm integrating around a closed surface. So like a sphere or something like that, or a box or something. So it's just a surface that is fully enclosed. So it's the surface area of some three-dimensional shape that is a closed box, sphere, cylinder, whatever, okay? And the sum, or excuse me, the integral of the magnetic flux density vector around this closed surface is 0. So this effectively means that whatever magnetic flux density field lines I have leaving that surface have to wrap back around and flow into the surface so that everything that flows out also flows in, and the sum of everything is equal to 0. So we've got our heads loosely wrapped around what those integrals mean, okay? So let's put these relationships into use by looking at some specific cases, okay? And these are probably classical cases that you visited in your prior electromagnetic field theory course. So the first one that we're going to look at, let's call this simply case number 1, is the magnetic field of a current carrying wire. So let's say that I have a section of wire like so, and we are just focused on this part of it here in the middle. So these ellipses effectively just mean that this is connected to more stuff. I don't want to have to draw the entire circuit because I'm only interested in what's going on for this particular piece of wire, okay? And let's say that I have a DC current flowing down the length of the wire, and I'm calling that DC current simply I, okay? So I'm going to draw a simple coordinate system for this, and I'm going to use a cylindrical coordinate system because to me, a long section of straight wire looks like a cylinder, and so I can probably exploit that symmetry to make the math less of a pain in the ass, which is exactly what I'm going to do, okay? So down the length of the wire, we are going to call the Z direction, and radially out from the wire, we are going to call that the rho direction, okay? So I'm going to apply that first equation, okay? So H dot dl is equal, excuse me, the closed line integral of H dot dl is equal to the surface integral of J dot d8. So I need to define some sort of contour around this thing. I'm going to choose a contour that is equidistant away from the wire all the way around, because that will make the math come out to be much easier, right? So effectively, my contour is just going to be some circle around my wire, and this circle has a radius of r. So as long as I go from the dead center of the wire out to my contour in literally any direction, I have gone some distance r. Okay? Are we all okay with that?
And that's a C that you wrote?
Yes.
Okay.
So my contour is defined by the purple curve, and it's literally just a circle encompassing my wire that is centered at the center of my wire, okay? And the contour bounds or provides the boundary for the surface S that I integrate over for my surface integral, which is the right-hand side of the equal sign. Now, I want to point something out here. This will be true for any surface bounded by this contour C. So it's probably easiest to think about it as a simple flat surface because we can figure out what the area of the circle is really easily. But there's nothing particularly stopping us from saying, actually, our surface is a hemisphere or something like that, bounded by that same circle. The math gets harder if we do that, but it's not wrong, it's just gross. So we are going to choose the easy route, but we don't necessarily have to. Okay. So let's get back to our math here, okay? So the equation that we're starting with is that Ampere-Circuital law. So we have the closed line integral of H dotted in to dl is equal to the surface integral of J dotted in to dA, okay? So our ultimate goal here is for us to actually solve for H, okay? So we need to think about some things, okay? So the first thing that I want to think about is what my expected behavior of the H field is going to be. Yes.
Dot for that equation. Are you talking about dot product or
Yeah.
just?
Dot products. Yeah, all of these are vector operations. So these are dot products. Yes. All right. So because my contour is equidistant away from my wire at all points, I have a stinging suspicion that the electric field strength will be the same at all points along that contour because they're all the same distance away from the source that's generating the field, okay? So H can be assumed to be effectively constant since we chose a contour that is equally distant away from the center of our wire, okay? So if H is a constant, that means I can pull it outside of the integral. So I'm just going to put H over here to the outside. And that's leaving me with now the integral of dl around that closed contour. So what does that integral represent? I'm integrating a differential line element around the circle. So the integral of dl is just the perimeter of the circle. Okay? So what's the perimeter of a circle? First, do we know? I mean, I guess technically we could figure out the diameter if we wanted to, but we have things in terms of the radius, right?
No.
Yes, I can kill it.
Hang on.
2 pi r, thank you very much. So H times 2 pi r, okay? Oh, I guess it is. I never even thought about it that way. I'll be damned. I'll be damned. I learn something new every day. Because 2r is d. Yeah, fair enough. Fair enough. Never even thought about it that way. Now I feel like a jackass. Great job, guys. All right. So 2 pi r in terms of the radius, which was what we're dealing with. Okay. So now let's look at the right-hand side. So we have a surface that is bounded by that contour C. And we're integrating over the entirety of that, and we're integrating the current density dotted into that. So effectively, and I believe I stated this earlier, that is simply what's the total amount of current passing through the surface? I. Yeah, that's it. It's literally just I. And so rearranging this thing, we would find that the value of our H field is equal to the current divided by 2 pi times the radius. So it seems like the further we move away from our wire radially, the weaker our field strength is, okay? Now, the H that I've written here is not a vector because we kind of hand waved away the vector relationships. And for what it's worth, the dot product is going to give us scalars. Hopefully you guys remember that. So it's not going to give us vectors anyway. So we need to figure out the directionality of what's going on. And we can use that Gauss's law for magnetism to figure that kind of stuff out, okay? So what we can use is effectively what's called the right-hand rule in order to figure out our directions. You guys are arguably familiar with that? Okay. I see all of you using your right hands, which is great because I have definitely seen students try to apply the right-hand rule with their left hand, and let's just say it doesn't go particularly well, okay? So let me draw another little picture here so we can sort stuff out, right? So here's our section of wire. Here's the direction of our current flow. And so by using the right-hand rule, which again, I think you guys are all loosely familiar with, if our current is in the direction of, excuse me, if our thumb is in the direction of current flow, then our fingers curl around in the direction of the field, right? So since my current is flowing from left to right, my fingers are curling around so that they're coming out of the page on top and they're going into the page on bottom. So I'm going to draw out of the page like this. So this is my H vector field. And what that's supposed to represent is a field line pointing out of the page. So effectively, we're looking at like the head of an arrow that's being shot right at us, okay? And then down here at the bottom, I'm going to have the symbol for something that's directed into the page. And so that's a circle with an X in it because it represents the ass end of an arrow being shot directly away from us, okay? So think of it like we're looking at the fletching or the tail feathers or whatever is of an arrow as it travels away from us. So another way that we could represent what's going on here is if we look at it from the direction of what's going on with the current, okay? So if we have our current flowing out of the page or towards us, then our magnetic field lines should be in a counterclockwise direction around that wire, right? So our field lines might look something like this. And if instead our current were flowing into the page, then our field lines would wrap around in a clockwise direction. Excuse me, like so. And as I mentioned previously, our Gauss's law for magnetism tells us that our field lines have to form closed loops because the total amount of magnetic flux density lines going into a surface has to equal the amount coming out for literally any surface. Okay. So this is what it looks like for a wire. So now let's think about something slightly different. We're just going to talk our way through this one more so than defining things mathematically, because this isn't something that we're going to give a shit about particularly, but we are going to use this thought to come up with something else, okay? So as an extension of this, let's think about what would happen if we had a loop like so. And let's say, for the sake of argument, that current was flowing around the loop in this particular direction. Okay? So what do we think the magnetic field lines are going to look like inside the loop? So I would argue that as our current is flowing around our circle, and I can't bend my arm so much that I'll break it, but effectively inside, they're going to be pointed up, and outside, they're going to be pointed down, right? So we should have field lines that are effectively doing something. Why is this drawing all slow? That was weird. Like this, okay? So inside they're directed up, and then they wrap around outside of that single coil, and then they wind up passing back through in the up direction, okay? So we've looked at that to have some basic understanding of how a coil works, because now what we're going to do is stack a whole bunch of coils effectively on top of each other to form a solenoid, which is something you guys are probably more familiar with, okay? So let's look at case number 2. Let me start this on a second page, if that's okay. So now we're going to look at the magnetic field of a solenoidal coil, okay? So I'm going to attempt to draw a solenoidal coil here. So let's say that I have some sort of cylindrical form. Like so. And then I wrap a wire around this cylindrical form. And let's say that my current is flowing in at the top, and it's flowing out at the bottom. And I am going to go ahead and add something right here so that we can see what's going on. So this dashed blue line right here is for the axis of symmetry of the form that we wrapped our wire around. And just for shits and gigs, I'm going to go ahead and define a coordinate system for this guy as well. So along the length of the cylinder is going to be our z direction, and out from the center of our cylinder is going to be our rho direction. So once again, we have cylindrical symmetry that we can try to exploit for things. Okay. So let's think about things a little bit here, okay? So if we're out towards the ends of our solenoid, things are going to behave pretty similarly to like if we just had a ring, right? So we're going to expect to see our field lines go out around the edge and then wrap back around or whatever. But what if we're in the middle of our solenoidal coil away from the ends? What might we expect the field to look like? So inside the solenoid, it should be directed pretty much straight up, okay? So let's figure out whether or not that's true, and let's do some math to make it, come out with some kind of useful result, okay? So what I'm going to do is I'm going to choose a contour in the middle of the coil that's away from the ends, so that I don't have to worry too much about what's going on at the ends, and we'll talk about that later. So let's choose a contour that looks something like this, okay? So I'm going to choose a rectangular contour, and I'm going to give it some names along its points. So I have one portion of this contour that is from A to B, and that is directly along the axis of symmetry of my solenoidal coil. And then I'm going to come out like so, perpendicular to those lines. So I'm just effectively forming a rectangular loop. And I'm making these perpendicular connections very long, such that line element CD is very far away from my solenoidal coil. Okay. So that's what these little things right here mean. This isn't a capacitor or anything like that. I'm just slashing the wire effectively to show that, hey, this part is a long way away. All right. So if we were to focus just on the current that's passing through our contour, we would have something that looks akin to this diagram, right? So this is kind of a zoomed in view of things, okay? So we would have that line element from A to B. Then we have our perpendicular bit that goes out to the line element from C to D, like so. And then at some distance away from line element AB, we would have all of those coils of wire stacked on top of each other. So based on the way that I drew the original figure, the current is actually going to be flowing into the board on all of those sections. So these are going to be little X's like so. Okay. And this forms N total turns for this particular length of our solenoid. All right. So let's go back to our original equation. Ampere's circuit law. So we have our closed contour integral of H dot dl is equal to the surface integral of J dot dA. And we're going to play around with this. So let's start with the right-hand side this time, because it's a little easier for us to wrap our heads around, okay? So what is the total amount of current enclosed by our contour? So every one of these sections of wire is carrying a current I. And there are N of them, so the total current is N times I. Is that okay? Yeah. So we're going to have something, and we'll get to that in a minute, is equal to N times I. So we have the right-hand side of this already figured out effectively by inspection. Okay. So now let's figure out what that something is. Okay. So I'm going to break my line integral up into 4 distinct parts, because my rectangular path has 4 distinct parts, right? I'm going to go from A to B, and then from B to C, and then from C to D, and then from D to A, okay? So that's going to look like the integral from A to B of H dotted into DL plus the integral from B to C of H dotted into DL plus the integral from C to D of H dotted into DL plus the integral from D to A of H dotted into DL. And all of this is equal to that NI that we just found. We okay with that? I've just broken that closed contour up into 4 parts, but I start and end at the same place, so it's closed, okay? So when we were discussing what the expected behavior was, we said that inside the coil, our field lines should be in the up direction, right? Based on what we looked at for a single coil. And then if we stack a bunch of coils on top of each other, inside the coil, it's going to be up. And then we're a long way away from the end, so we don't really care about how it curves and all of that kind of stuff over there. Okay. So what can we say about the direction of our field vector H and the direction of our line element AB? So I'm only concerned about the directions right now. Okay, we have to take into account the fact that we are doing a dot product here, and this is actually going to matter for this particular geometry, right? So
is it going?
the direction of H is up, right? What is the direction of line element AB? Also up. So you guys are maybe slightly familiar with dot products. When I have the dot product of 2 things that are in parallel, what does that mean? I literally just get to multiply them together. Why is this being a bit? No, I'll make it work. That's too obvious of a solution. Yeah, makes way too much sense. Ooh, good God. All right, this is fine. Okay, so for what it's worth, because it's probably been a hot minute since you guys have seen this, so I'm just going to put this over here in light purple, okay? So X vector dotted into Y vector is equal to the length of the X vector times the length of the Y vector times the cosine of the angle between the 2 vectors, okay? So when I have 2 vectors that are in parallel with each other, the angle between them is 0, and the cosine of 0 is 1. So effectively, when H and our differential line element are in the same direction as each other, we just multiply H times the length of the line, okay? So that means that this first term right here literally comes out to be H times the length of line element AB. Are we okay with that? Okay. Now let's look at our next part. Okay. So now we have our H vector dotted into our line element when we're along the path B to C. So our H field is still up, but our line element is now directed to the right. So what's the angle between them? 90 degrees. What's the cosine of 90 degrees? 0. So this second term literally just goes away because the field and the line element are perpendicular to each other. Now we've got this part for CD, okay? So we've got another situation where our field and our line are parallel to each other, but I've chosen this line to be really far away from the current. And what do we know about magnetic field vectors? They are weaker as we go far away. So if I choose my line element to be so far away that the H field is effectively zero, this third term also goes to zero. And now we've got a fourth term. And this is for what's going on with line element AD, which is once again perpendicular to our H field. So this bit goes to zero, and we're left with just N times I. Okay. So from this, putting all of this together, effectively, what we find is that the closed line integral of H dotted in to DL is just H times the length of the distance inside the coil that we're choosing, and that is equal to N times I. And so we can rearrange that and say that H is equal to N times I divided by L, and it will be in the Z direction. And I'm going to put a caveat here for 0 is less than rho is less than R, meaning effectively, this is what it looks like as long as we're inside the coil, because these are the boundaries of the coil, right? So we're going from 0, which is the axis of symmetry, out to where the coil exists. Anything past that, we don't really know what's going on because we set up our system of equations to not bother about that for now. Okay. So what we have here then is an equation that tells us that inside the coil, as long as we are far away from the ends, the magnetic field strength is constant. So it doesn't matter if we're on the axis of symmetry or out to the sides, we have some constant amount of magnetic field inside of our coil. So what our coil is doing is effectively concentrating our magnetic field, which I believe we talked about in the 280 class last quarter. Okay. So the next thing that I want to talk about is what the influence of this cylindrical form has. And that's going to depend on what type of material it is. So we need to very loosely review magnetic materials. Okay. So let's talk about that for the next couple of minutes. Okay. So the structure inside the coil is called the core. And the material the core is made of can affect the magnetic field behavior depending on what type of material is used. So we're going to talk about 3 different types of materials today. Okay. So the first are diamagnetic materials. So diamagnetic materials experience weak magnetization in the presence of an external magnetic field. So let's talk about this just really quickly because there's something kind of buried in here that may not be intuitively obvious. If we go back to our picture of a solenoid here real quick. So we've got a wire wrapped around something, okay? So what do we control in this system? The amount of current that's flowing through that coil, okay? So that coil is forming effectively an electromagnet, right? Because anytime that we have current passing through a medium, we generate a magnetic field. And so if we control the current, we control the amount of magnetic field that's generated in the system. Well, those magnetic field lines are passing through this core material. And depending on what the material is, it's going to behave differently. So we are effectively subjecting this core material to an external magnetic field that we control by creating this electromagnet. Okay? So for diamagnetic materials, we have a very weak magnetization, which means they don't particularly like to get magnetized too much. Okay. So they produce, or diamagnetic materials produce, a magnetic field in the opposite direction to the external magnetic field. So they tend to decrease the net field. So if we were to put a diamagnetic material inside the core of our coil, the field would be weaker. Now, this absolutely has its uses, okay? How many of you guys have heard of maglev trains? They use diamagnetic materials because effectively the induced magnetization field is in the opposite direction. What do we know about magnetic fields in opposite directions? They repel each other. So if we pump enough current through our coil, we can actually generate a force that causes things to lift off. And then we have to use a time varying field to make it drag it along a section of tracks and stuff like that. Okay. So diamagnetism is actually really, really neat, even though for most applications, it seems like it's going to be a bad thing. It can be utilized for very specific things to do some incredible stuff. Okay. So some examples of diamagnetic materials would be like water, wood, so organic materials, but also glass, salt, okay, copper, gold, and silver. So some metals are diamagnetic. That's why copper is very commonly used as electromagnetic shielding material, right? So effectively, it provides a very good conductive path to get electric fields away and provides a response that is opposite to any applied magnetic fields that prevent them from getting inside the material that's enclosed by the copper Faraday cage. So that's the reason why copper is used in Faraday cages. Gets the E fields away by surface conduction of the effectively current flowing through it, prevents the H fields from entering because it's a diamagnetic material. So it generates a response to tend to negate it.
So water is like, if you forget something that this is cover on the water.
If you put enough of a field on it, sure, but you've also got to worry about being able to split your water atoms, which happens relatively easily.
That's why hoverboards are.
So what I mean by splitting your water atoms easily, so it doesn't require a ton of energy to convert liquid water into gaseous hydrogen and gaseous oxygen. There are fuel plants that effectively do just that. So I don't know, like, there was a demonstration by some guys that won the Nobel Prize in, I want to say it was the mid 2000s, 2005 to 2008 or something like that, where they effectively used diamagnetic properties of organic materials, which is mostly water, to levitate dead frogs.
This is what we do for science.
Yeah. So the short answer is yes, you should be able to do it. Yeah. Caleb.
Alright, so explain to me.
So I've always wondered about this because I always used to see those like videos of like the little things you can buy and it like makes the water drop just like goes up instead of.
Probably some sort of magnetic
Yeah,
interaction.
Okay, because
I don't know for sure because I'm not 100% sure of what you're talking about, but
Like the
seems
things in museums where like, you like they have like a water tower, you see like going like.
I think that's vibration. Yeah, that's.
the vibration. So that now.
Instead of like your water droplets just dripping down, so it's an illusionary thing of it looks like it's going up.
so that's some sort of using like the index of refraction of the glass or something like that, bending the light rays, or I'll have to look into it. I don't know.
So explain to me the hoverboard from Mexico.
That's a movie prop. It isn't real. Explanation over.
That's it.
Explain to me how we can make this a reality.
Yeah. All right. So diamagnetic materials we've talked about. Now let's talk about paramagnetic materials.
Just like put a massive magnet under the entirety of the water. And then you can have some.
Just hearing you talk, the the Earth itself is a giant magnet already. That's why we have a magnetic field that prevents that keeps our what's the word? No. So the Earth's magnetic field keeps effectively like solar rays, like the solar discharge and all that kind of stuff from literally just obliterating our atmosphere constantly. It actually, an interesting thing, I'm getting distracted so damn easily today. So the polarization of Earth's magnetic field actually changes over time. So like our magnetic north a couple of 100 million years ago used to be magnetic south and all of that kind of good stuff. I would be interested, I don't want to live through this, to see what happens when Earth's magnetic field changes polarities, like if that allows effectively electromagnetic radiation and all that kind of stuff from the sun to pass through for that brief time, and does that just obliterate practically all life on Earth or not? So it's an interesting thought experiment that I hope to not live through.
Like a gradual change, or is it like an instant change? Like,
I honestly don't know, because it happens so infrequently, but there are.
Find that.
like, is it gradual, is it instant, or is it like a on, up and in reverse?
I don't know.
It's like trying to hold back a mouse trap.
Yeah.
Before you start the magnet, you just go out.
Something like that, I know there was a movie once where it was like the ozone layer, like for a brief moment of time, like evaporated or something like that, and it like stuns, right, it's just like melted through stuff.
So I mean, that's effectively what I think what happens
Yeah.
is that so we don't have that magnetic field blocking everything else out. If we allow that to come in, then yeah, the Earth's atmosphere is going to burn off rather quickly and everything's dead.
Yeah.
So anyway. Yeah. All right, I have opened up too big of a dumb bag of cats. Let's get back to this. Paramagnetic materials express slight magnetism in the presence of an external magnetic field. So they produce a small magnetic field in the same direction as the external field. Goodness. And tend to enhance the net field. So some examples of paramagnetic materials are aluminum, magnesium, and tungsten. So iron is what we're going to talk about next, which is a ferromagnetic material. So for paramagnetic materials, they exhibit very weak induced magnetic fields. So this is part of the reason why you can't use, like, magnetic separators that are used in recycling can't be used to get aluminum cans out because you can't use magnets to attract the aluminum cans to them. So it does a great job of picking up things like tin, steel, all that kind of good stuff. But aluminum just kind of sits there. So effectively, the interaction is so weak that the attractive force isn't enough to bring it out of the bin or whatever.
Also, the reason why you can't go.
That is an entirely different thing. And also, so here's another damn tangent, Jesus Christ. Go open up your microwave door. There are metal screws in it. You are microwaving metal every time you turn the damn thing on. So microwaving metals has to do with a lot of things, and I'm not encouraging anybody to go blow up their damn microwave. I want to be really, really clear about this. But a lot of, no, don't do it at your friend's house. Don't go to Tolliver and blow up their microwave or anything like that. Okay. But so a metal reacting to microwave radiation actually has a lot more to do with surface roughness than anything else. So if you were to put
I put that.
How we get a aluminum foil on?
so if you put in like a really, really crumpled up piece of aluminum foil or something like that, like it is going to spark and shit like absolute crazy. But if you were to put in a flatter piece, it wouldn't have as violent of a reaction, kind of thing. But anyway, so no, just to say, like, you don't realize it, but you're microwaving metal every time you turn your damn microwave on.
Well, That's my aluminum
So
ball.
are we gonna talk about like these things in terms of like actual equipment?
Yeah.
Okay.
Yeah.
So,
We're just taking forever to get there for what it's worth, but yes,
Theoretically.
it's not remote. I'm saying that the interactions will be less violent the smoother it is. All right, ferromagnetic materials. I'm gonna have to like put earplugs in and just read my notes at you. So ferromagnetic materials experience strong magnetization, meaning that they are very easy to magnetize in the presence of an external field. Okay, they produce a large magnetic field in the same direction as the applied field. So they, goodness, greatly enhance the net field. So effectively, ferromagnetic materials are the types of materials that we typically associate with what our magnets in our homes and all of that kind of stuff are made from, right? So some examples would be iron, cobalt, and nickel, and alloys made from those things, which is stuff like steel and tin and whatnot, okay? So these ferromagnetic materials, and I'm getting a little bit ahead of myself here, but it'll be okay because this is actually kind of on topic. Generally already have some type of magnetic domains within them when they're formed. So they have very, very weak magnetism already. So they're like permanent magnets. But when we subject them to an externally applied magnetic field, it tends to align those magnetic domains, and the material has residual magnetization, which effectively keeps it being magnetic. So that's how we make magnets, is we place metal pieces made of some combination of iron, nickel, and cobalt in the presence of an external field, and it magnetizes them, and then it keeps those magnetic properties, and that's why they stick to our refrigerators and all of that kind of good stuff. Doesn't necessarily have to be solid pieces either. So like those flexible magnets that you get from like the pizza place and all of that kind of stuff that stick to your fridge, that's actually like a type of iron powder that is suspended in a medium, and you magnetize that and it sticks to your fridge. Brock, you had a question, comment, or concern that I may choose to ignore.
Here's about, so you can use two magnets and you can levitate an object. Well, that's floating it in the air, so that's applying a force to the object. So what I'm curious about is where the energy for that coming from, or is it using energy? It's just magnetism and kind of just like.
So that's what we're going to talk about once we get through, like, this will be shortly after I think the Christmas holiday, is we're going to talk about how stored energy in magnetic fields can generate physical forces or mechanical forces and all of that kind of good stuff. So that's actually kind of the purpose of this class, is to explain how that behaves, because that electromechanical energy transduction is what we use to make electric machinery. So we'll get to that soon. Okay. All right. So the E's of magnetization of a material, so effectively how easy it is to magnetize something, is known as its permeability. Okay. Permeability has a symbol mu, so lowercase mu, okay, which is defined in the following relationship. And this is a pretty straightforward one. B, our magnetic flux density vector, is equal to mu times H, our magnetic field intensity vector. Okay. So this is an interesting relationship because H is the thing that we get to control by the amount of applied current, and B is something that happens as a consequence of the medium that we are trying to magnetize. And they're related to each other by this permeability constant, okay? I say constant, permeability isn't necessarily constant or even a linear quantity for materials, and we'll talk about that later, and we'll get to look at fun things like BH curves and all that kind of jazz, but we'll sort out what that means in a little bit, okay? So for a particular material, its permeability, mu, is typically identified relative to the permeability of free space or a vacuum, as mu is equal to mu r times mu naught, where this mu r, that I can't spell, is the relative permeability. And that is a dimensionless quantity. So it's literally just a number being scaled by the things, right? And then mu naught is the permeability of free space. And this has a numerical value, okay? So this is 4 pi times 10 to the negative 7 henries per meter, which is the same thing as 4 pi times 10 to the negative 9 henries per centimeter. So effectively, the higher that mu is, or the higher that mu r is, the easier it is to magnetize a particular material. So we can quantify materials based on their relative permeability, okay? So when mu r is less than 1, these are our diamagnetic materials. When mu r is exactly equal to 1, we have a vacuum, or literally nothing. When mu r is greater than 1, we have paramagnetic materials. And when mu r is much greater than 1, and I'm talking about in the thousands of times greater than free space, then we have our ferromagnetic materials. So, tying things up here. For most of the applications, we'll deal with in this class we want to produce the largest magnetic flux density. And I'm going to put here B because that's the B field. As possible with the smallest coil current. So this is effectively the H field that we control. So high permeability materials are used. A consequence of this choice is that a large portion of the magnetic flux is confined to the core. So effectively, if we were trying to design something like an electrical transformer, where we want to be able to effectively magnetize it easily so that we can store the most amount of energy in it with the least amount of effort, we would want to use a very high permeability material. So that's why our lower frequency transformers, like those that are used in transmission and distribution networks, are typically iron core transformers, because it's so easy to magnetize them. We don't lose a whole hell of a lot of energy in the magnetization and demagnetization process as we transmit energy from the primary coil to the secondary coil. For other applications, though, we don't necessarily need or to have that level of efficiency, right? All right, so let's revisit our solenoidal coil. So let me redraw a coil here. So we've got our core like so. We've got our wire wrapped around it. Like so, where we're passing a current I in this direction and it's returning in this direction. And now I'm going to draw our field lines for this system, okay? So we know that inside the core, effectively we have constant values of field lines and they're all directed up, right? As we get towards the edges, we should expect to see them tend to wrap around like so in order to form closed paths. So we are going to revisit some things really quickly, okay? So our magnetic flux density vector B. So this is a measure of effectively how much our core material compresses or confines our field into a particular amount of space, right? It is a density vector, and so it's effectively saying we have so many magnetic field lines passing through a particular area, okay? So we are going to define B in an alternative way as phi B over A, where this is our magnetic flux, and this is simply our area. So for our solenoidal coil, we can use this definition to say that our magnetic flux density vector magnitude will be simply phi b over pi times the radius squared for regions inside the coil. Okay. And this will be approximately equal to mu times n times I over L, also for regions inside the coil. And so just for sake of argument, I did not pull this out of my ass. If we go back and look, we found that our H field was Ni over L, and we're simply multiplying that by mu to get our B field, because B is equal to mu times H, right? So we've already effectively derived that relationship. Now, for areas outside the coil, this would look like phi B over the total area outside the coil. What's the total area outside the coil? Yeah. So what's phi B over all the area? 0. So outside of our solenoidal coil, our magnetic flux density is effectively 0. And since we know that H is equal to mu, B is equal to mu times H, that effectively justifies what we got earlier of saying, it probably doesn't matter, so I'm just going to choose a distance really far away. All right, so if our coil is wrapped around a high permeability core material, then the flux density B is much higher inside the core than in the region of space outside the coil. So our core is essentially concentrating the magnetic field lines until we allow them to leak out at the ends. So is there a core shape that we can use that will eliminate this flux leakage? So we already have a rod, but what if the rod closed in on itself, like a donut or toroid, right? So that's what we're going to look at next. So the magnetic field of a toroidal coil. And this is the basis for how effectively we design magnetic circuits, which are a subsection of transformers and all of that kind of good stuff, okay? All right. So I think I'm not going to have enough time to get into the in-class assignment for today and all of that kind of good stuff, which isn't really an issue, but we'll cover this relatively quickly and then we'll knock off for the day. So-
Magnetic field.
Toroidal coil, Toroidal. Toroid is a fancy word for donut. Or for the shape of a donut, I guess would be a better way to describe that. You should, you will make the, dozen glades, toroids, yeah, okay. All right, so I'm going to try to draw concentric circles here, which is going to be difficult for me because I can rarely even draw reasonable normal circles. So something like this. So here is my inner area. All right, so this is my core material and it effectively is going to extend into the page or out of the page. It doesn't really matter, but it's not just a flat circle like this. It's forming a donut. So it could be rounded or it could have a square cross-sectional area. It doesn't particularly matter, but it is just a closed three-dimensional surface that we can imagine if we took a rod and folded it in around on itself, we formed this thing, okay? So it's got some radius that I'm going to call R1, like so, and it has some radius that I'm going to call R2, like so. And for what it's worth, I'm going to define our cross-sectional area as circular for this particular example, but it literally doesn't make that much of a difference. And we'll talk about how to incorporate different cross-sectional areas in a little bit, okay? So this is our cross-sectional area. Okay. So I'm going to wrap a coil of wire around this guy. Like so, and I'm going to pass some current I in this direction and let I flow out in this direction. So based on the direction of these windings, let's see if we can figure anything out. And actually, I probably should have. So we talked our way through the field direction for a solenoidal coil, based on what we got from a single ring. But there's actually an easier way to describe that, and that'll help us with this thing as well. So let me scroll back up here so that I can just show you what's going on, okay? So this is involving using the right-hand rule as well. So effectively, whenever we have a coil of wire, if our fingers are curling around in the direction that current is flowing, then our thumb is pointing in the direction that our field will orient itself, okay? So it's the exact opposite of when we have a straight wire. When we have a straight wire, if our thumb is in the direction of the straight wire, our fingers wrap around to tell us the direction of the field. Well, when we have our current or our wire wrapped around, our thumb tells us the direction of the field. So it's just literally the exact opposite relationship. Okay. So if we have a toroidal coil, this is just like we have our wires wrapped around and our thumb is going to tell us the direction, but now it's curving around like we had with our loop, okay? So since our current is flowing in and our wire is wrapped around in this way, what we should expect is that our field lines are going to be flowing clockwise around this guy based on the direction of the winding and the direction of the current flow and all of that kind of good stuff. Okay. So we have some idea of how our field directions are looking. So now let's figure some stuff out, okay? So we need to define a contour that encloses some current, okay? So we have to be fairly careful about this. Okay, so let me explain what I mean. So ultimately, I'm just going to write our equation over here on the left-hand side. We know that H dot DL is equal to J dot DA, right? And so if I want to figure out what H is, I effectively need to make sure that my contour encloses some current, okay? So if I were to choose a contour inside like this, I enclose no current. So this doesn't get me any information whatsoever. Or a different way to think about that would be, since no current is enclosed, the H field has to be 0 in this region. If I put my contour anywhere around the outside, I have currents, an equal amount of current flowing into the board and an equal amount of current flowing out of the board. So once again, the total amount of current that's enclosed by my contour is 0, which allows me to infer that my H field outside of the toroid is also 0. So it seems like I need to make sure that my contour is inside of the toroid in order to have any amount of current enclosed that isn't 0. So I'm going to choose my contour to be exactly in the middle. Okay. So this is what we're going to call our average, Jesus, I can't spell today. Flux path. So on average, the total length of this contour is the length that the magnetic flux travels as it circulates around this toroidal structure, okay? And so this is just some distance. Let me use I'll use this light green, okay? So this is what we're going to call some distance R away. And for what it's worth, if we want to be the exact average, this is just going to be R1 plus R2 divided by 2. All right, so using our equations, so let's start over here. H dot DL is equal to J dot DA. So let's make some inferences based on what we've learned today. Okay, let's start with the right-hand side again. So what do you think the total amount of current enclosed by our contour is going to be? I times the total number of times we wrap the wire around this section of material. So it's just going to be Ni again, right? Since our contour was defined to be exactly in the center of our toroidal shape, I feel like it's going to be constant all the way around because it's a constant distance away from that center point. So the H value is going to be constant. We know that H is in the same direction as our contour. So H dot DL is just the same thing as H times L. So what's the total length of our contour here? We could call it HL, but we could also call it H times 2 pi R, same thing though, right? So HL or H is 2 pi R, and those are the same thing where that L, let me write this a little bit better. So HL is equal to H times 2 pi R, and this L is what we're going to call the length of the average flux path. So we're actually a little bit ahead of the game because this is how we're going to analyze other shapes by putting things in terms of average flux path, okay? So from this, we can rearrange things and we can see that our H field is Ni over 2 pi R, which is the same thing as Ni over L. And from this, our B field is just mu H. So that would be mu Ni over 2 pi R or mu Ni over L. They are 4. So it just means I did a little bit of algebraic rearranging into the thing that I'm actually looking for. Because my ultimate goal here was to define H as a function of the geometry of the system. Okay. And our distance away from it. All right, so the last thing that I want to do here is I want us to define our magnetic flux. So our magnetic flux, phi B, is just going to be the strength of our magnetic flux density vector B times the cross-sectional area of our toroid. Because we know that all of our flux is confined to the inside of the toroid because there was no H field in the center area and there was no H field outside. Okay. So this means that our flux could be written as N times I times mu A over L. Now, you may be asking yourself, why the hell I bothered to write this in such a weird ass way? And that is a fair assessment, okay? So let me explain that to you. Okay? So our magnetic flux is what's flowing around this system, okay? So we can think of it as something analogous to electric current, which we know in a simple electrical system flows around our circuit, okay? So this is kind of like I. Well, Ni is what's known as a magnetomotive force. So it's what's creating the flux that's flowing around our circuit, right? Because if we don't have any current flowing, we don't have any flux moving around in our system, because we know currents generate magnetic fields, and the total amount of flux is just related to the total amount of current flowing in our system, right? So this is analogous to voltage in an electrical circuit. And so this thing right here looks like effectively the inverse of resistance. So we now have an Ohm's law effectively for magnetic circuits. Ni is equal to phi b times L over mu A, or MMF is equal to flux times what we're going to call reluctance. And this is where we're going to stop for today, because there's only a minute and a half left of class anyway. So we'll probably kick things off by working today's in-class assignment at the very beginning of next class, just so I can show you how to use some of these relationships. And then we'll get into more interesting things. All right. Thank you guys for your attention. Glad to see you all again. Hopefully you had a reasonably good time putting up with my bullshit.